All right, so I am in record mode. So what I'll be doing is, okay, that was yesterday's class. Here is today's class. I'll be doing a recording. So you get to hear you can count how many times I say or how many video typos I make. It's going to happen. But you will have a live presentation of at least an example or two from each one of these items on our to-do list. You are invited to, so you've got it today, and if you want, there's similar questions you can look at from yesterday. So I think, to the extent that your ambition and your initiative is there that you want to see them, then at least it's available to you. All right. So let's hop right into it. And by the way, if you have questions, I can edit you out. I cannot have your likeness, and I don't even think your voice is supposed to be on a recording. I'm just going to be ultra safe until I hear otherwise. So if you have a question, don't hesitate. I will edit you out when I make the video. So real quick, integration by U substitution. This was a PowerPoint that I made back in like 2008, and it's the software has since updated, so I can't edit it anymore, and it's a little glitchy. But the questions are good, so I'm gonna go with them. So as soon as it opens. Now, what I want you to think about is a couple of the U substitutions are what I called yesterday walk in the park easy, and a couple of them you got to write out. So I do want you to get to the point where you are starting to do some of these in your head. All right. So I've got 4 pages here. I've got the blue page, the green page, the yellow page, and a tan page. Walk in the park easy would be number 1 from the blue page. Would you see if you can do that, please? I will set up the one at the bottom. In each of them, by the way, you're trying to work your way towards a power rule of integration. You guys might want to mute yourselves. I'm hearing a little bit of noise in the background. If you were the one doing that. All right. Walk in the park easy is the one at the top. What I'm looking at this is I'm looking to do a power rule with that thing, 2x to the third plus 1 is what I would use as my u. And in order to execute that power rule, if you go through the u substitution, if you use u equals 2x to the third plus 1, you're going to need the derivative of that somewhere in your integral. Well, 2x to the third plus 1, its derivative is 6x squared, and there it is, right there. So it resides there. And in order to execute this integral, just apply the power rule to that quantity, 2x to the third plus 1. So you go to 2x to the third plus 1 to the 6th over 6 plus c. Done. All right, that's as much writing as I would do for this one. And you might say, well, where did the 6x squared go? Well, then I'll counter by saying, well, where did the dx go? Where did the integral sign go? It's kind of a layman's answer might be it's just a byproduct of the process of integrating. If you want the explicit answer, then continue to the u substitution. You'll see that it canceled out. Now, as I look at the second one at the bottom, I don't think this is walk in the park easy. I think it takes a little bit of writing, at least for me, in order to do this integral. I have done the u substitution. Again, my thing, I'm looking to do the u substitution. What I'm looking to do is I'm looking to apply a power rule of integration. And what I'm looking to apply it to is this, I keep using the word thing, this thing in the denominator. Okay, well, that thing in the denominator, its argument is 2x to the third minus 3x. The u substitution is laid out below. If I were to now write the u substitution with the information I have, I would have the integral of, excuse me, I'm going to factor that numerator. Instead of 8x squared minus 4, I'm going to write it as 4 times 2x squared minus 1. Okay, and then that thing in the denominator was something to the 1/2 power. So u, I'll just write it as the square root of u for now. You know where it's going. It's going into the numerator as u to the negative 1/2. Our dx is coming out as du over, well, let me factor that 6x squared minus 3. It's 3 times x squared minus 1. Wait, did I? No, 2x squared. Factor 3 out. Come on, Dan. You end up with 2x squared minus 1. And if you size up what we've got so far, 2x squared minus 1's cancel out. And we can rewrite this thing. In the 4/3, it doesn't matter where you put it. Let's take it outside. We'll call it 4/3 times the integral of u to the negative 1/2 du. And this integrates to 4/3 u to the positive 1/2. We're adding 1, not subtracting 1 when we're integrating. And I do acknowledge that gets confusing. Over 1/2 plus c. And there you go. The last thing you have to do as far as housekeeping is remember to put the what you substituted what you replaced with a u, you got to put it back. It's like cleaning up after yourself. All right. So one of these was walk in the park easy, and one I think prudence would require you to write that one out. All right. So let's see. This guy, I had to say, this is what happens when the font, when your software gets old. Number 5. Can you do that one in your head? Give it a shot. I'm going to set my timer for 30 seconds. Got my cell phone. Let's see. Clock. Timer. 0. By the time I set this, 30 seconds will elapsed. My challenge to you is, can you do this in your head? Can you do it accurately? And can you do it without stress? I mean, if you don't feel confident about it, my God, just write it out. Well,
Mr. Murphy.
Yes, sir.
How do you decide which, like for number 5, how would you decide which part of the fraction you're going to substitute for u?
I'm not trying to be a wise guy here, but a little bit of it is learning to recognize the dead ends. And you got to take some dead ends a couple times. And once you've gained that experience, it's like drive. Oh, time's up. When you drive a car, you've been a passenger in a car for 16 years, but when you get behind the wheel for the first time, it's kind of nervous, right? And you learn by experience, you get to be a better driver. What I'm looking at when I see number 5, I see something to the third in the denominator, and immediately where I'm going to is, let me rewrite this thing. Where I'm going to with this is the integral of the sine of x to the negative 3 times the cosine of x dx. Is it jumping out at you now that you want to do a power rule integral and you want your u to be the sine of x? Okay. Now, as you're looking at this, I might say, well, it looks like maybe this is one of those logarithm integrals. And I would agree if it were, let's see here. If it had been the integral of the cosine of x over the sine of x, we know that's the cotangent function, which we did this last week, actually. I mean, these look very similar to each other, right? And if you have this one, you got to do a natural log, but if you've got this one, you got to do a power rule. And how do you see that? It's just, again, I'm going to go back to what I said before. If you tried to set this up as if you tried to set number 5 up as a natural log rule, you'd have hit a dead end. And you got to recognize that even though you do nothing wrong, you can't execute the integration process. And if you can't do that and done nothing wrong, look for another path. Hopefully you can see that this, if you want, you can do the U substitution. I would go right to here. The sine of x to the -2 over -2 plus c is the answer to that one. Okay, where'd the cosine go? Where'd the dx go? Where'd the integral symbol go? These are all byproducts of the integration process. Okay. Okay. Let's do one more. Let's see if there's one. I just want to do the quote easy ones for now, because this is the real challenge here is, can you do these in your head? And I think walk in the park easy is number 7. I'm going to set it for 30 seconds. All right. While you guys are doing that, I'll set up number 8. That's not walk in the park easy. I would do that one with pencil and paper. 30 seconds have expired. This is e to the 3x. Hopefully you guys recognize that's an exponential integral. Base e is good times for you because it's a lot easier than having to remember where's the ln of the base go. So this just becomes e to the 3x. What I need in order to execute this, I need the derivative of that 3x to be in the integral. It's not there. So I put in a 3, but you can't just arbitrarily multiply something by a factor of 3. You got to balance it out by multiplying by a factor of 1/3. So what you end up with is you've got this e to the 3x times 1/3 plus c, and that's your integral. All right. Now, number 8, this is not one I would do in my head, but if you're doing this one, what's your strategy? I see 2 candidates. I think you could make a viable argument that this is a rule. You want to use a natural log rule of integration because all the stuff is in the denominator, right? I think you can also make an argument that you'd want to use the power rule because notice one of those things in the denominator is to the second power. So your choice, which one? Think in your head. I don't want to expect you're welcome to respond over the Zoom, but I want you to think in your head, which strategy would you use to integrate that? A natural log or a power rule with U sub? If you said power rule with a U sub, you are correct. Let's run this through real quick. Du dx. I'm not going to talk. I'm just going to do it. Here's the U substitution. So I know these are definite integrals. I'm ignoring the bounds. I just want you guys to see the U substitution process. So let's put in what we've got for our U's. We have the integral of 1 over, well, that x is still there. The ln of x has now been replaced by a U to the second. And that just looks horrible. I'm sorry. 1 over x u to the second, and then our dx is coming out in favor of an x du. And there it is. So those x's cancel, and what we're left with is an integral of u to the -2 du, and that is u to the negative. Remember, we're adding 1 when we integrate. U to the -1 over -1 plus c. And to finish this off, I would probably write it as -1 over ln of x plus c. Is that right? I don't have the answer key with me. I'm going to take the derivative real quick. Is that right? If I were to quotient rule that, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's equal to 1 over x over the ln of x squared. Yeah, and if you were to simplify that, those guys are the same. All right, so a little bit of review on U substitutions. Some of them very easy and some of them have a challenge to them, all right? Okay, I think we move on to the next topic. And again, you have access to this PowerPoint through the Zoom notes from today. If you want to do the rest and ask me about them, I'm more than willing to talk to you guys about them. But we should move on. Next up, a slope field quiz. Back in the day when I used to give quizzes and tests with greater regularity. I am looking forward to a retake of our derivatives quiz. It's going to be similar in format to what you guys took last week. You will get that quiz the next time I see you live. So if it's Thursday, as I hope, you'll get it Thursday. Good Lord, if it's next Tuesday, it's next Tuesday. My intent is to not take up our time with excessive review and test taking, but I do think occasionally what's called a formative assessment is required. It tells me where you are and how I'm doing, all right? Okay, this one has got a lot to it. The definite integral, or the differential equation I'm using is dy dx equals x minus 1 over 2, and I want to walk through you with a slope field. This is in fact the same slope field that I used yesterday. The only thing that changed is the initial condition. I think I used 0, 1 with yesterday's class. We're going to give it a shot with 1, negative 1. We're going to go through, we're going to just sketch the slope field. I'm going to walk you through an Euler's approximation. And then this is something that is called a separable differential equation. We're going to find the general solution and use the initial condition to get a particular solution. Wow, that's a lot of vocabulary. All right, let's start off by just drawing the slope field. What this is telling us is it's telling us the instantaneous rate of change of a function, and it tells us wherever we happen to plug in values. Notice there are no values of y here, so y does not affect the slope of this. If I wanted to know, let's say, I always choose an easy number to start with. I would choose 0. So dy dx at x equals 0. Y doesn't matter, so I'm just going to generalize it. At any x equals 0, at x equals 0 and any y, we end up with, well, 0 minus 1 over 2 is negative 1/2. So whenever x is equal to 0, now what you do is at x equals 0, which is along the y-axis, make a tiny little linear equation whose slope is about negative 1/2. All right, and let's try another point. Let's go to x equals 1. So we've got dy dx at x equals 1 and any y. That's going to be 1 minus 1 over 2, which is going to be 0. All right, so we've got ourselves a 0 here, and it's about this time I might be curious what it is we're trying to build here. Notice that the differential equation is a linear equation, and the kinds of functions that get linear equations as their derivatives are quadratics. So I'm looking that we're probably building a slope field of a family of quadratic functions. All right, let's keep going to the right. Let's try dy dx equals any x equals 2. Again, the y's don't matter, so we've got 2 minus 1 over 2. So I've got a slope now of positive 1/2. And sure enough, it looks like at x equals 2, we've got a 1/2 as our slope. It looks like we are kind of rounding that parabola up the right side. And I think you guys get the idea. If I were to use x equals 3, we'd have a slope of 1. If we had a slope of -1, -1 minus 1 is -2. We have a slope of -1, and hopefully you guys can see the family of functions whose derivative is x minus 1 over 2. It's all of these parabolas. So our charge next is we're going to do an Euler. Now by the way, yes, we can integrate this and we can find the general solution. What you guys are going to find is that there are situations in which we can't, all we've got is the differential equation. And based on what we know right now in this class, you can't get the integral of it. I'll speak to that in just a second. But before I erase this slope field here, if we have an initial condition of 1, -1, well, that resides right about here. So 1, -1. So if we were to just let ourselves, like, this is where we jumped into the river, and we'll let the current, where does the current take us? To the left? Where does the current take us? To the right? That's an approximate graph of the particular equation when x equals 1, -1. All right, so let's do a Euler's method. Let's see if we can get an approximation. I'm going to see how far we can get with that. I don't know if I'm going to do all 4 increments. I'm concerned about time. The only thing I need to write down is I do need to write down that our differential equation, our dy dx, is x minus 1 over 2. I'm going to scroll up to make some room. Okay. Make room. There's got to be a better way for me to do this than all this erasing. Okay. The thing with Euler's approximation is the key is you gotta be organized. It's more a matter of bookkeeping than mathematical insight, I think. So what you want to start with this is you're basically going to have 5 columns. And I looked ahead. I saw Kim Thomas is going to present this in like somewhere in the middle of the next unit. The MyAP folks get around to finally talking about Euler's method. And she uses a different way, and I watched it, and it's different. I think this way is easier. I got this out of your textbook. Basically, you need 5 columns. You need the point you start, which is an xy. And we were given that point. It is right there is where we're starting. So let me enter that. We're starting at 1, -1. All right, the next thing you need is your dy dx. And your dy dx, fortunately I wrote that down so I don't have to remember that it was x minus 1 over 2. All right, so what we do is we apply the point we have, 1, -1, and we plug those numbers into our differential equation, which is 1 minus 1 over 2. The only contributor to this was the x value. There's no y value. So we end up with our dy dx at this point is equal to 0. Right? The next columns you need is you need a delta x, and then you need a delta y. Okay, the delta x, we're using increments of 0.1. And every quiz or test I've ever written, that's been my default delta x. So we've got 0.1. Now, what is delta y? Well, let's talk theory a little bit. Dy dx, you guys have come to know and love that as the derivative. It's the rate of change of y with respect to x. And we're looking at this as far as very abstractly when the difference becomes infinitesimal, non-measurable changes in y over changes in x. In fact, that x, like the change in x is approaching zero. Well, delta y and delta x is living in the world that you and I live in. This is not the world of infinitesimals. This is the world of measurable amounts. So we're using this as an approximation. If we have not hit that limit as x approaches zero, we've got ourselves a measurable change in y and a measurable change in x. So instantaneous versus measurable, I guess maybe that's how you want to think of it. Well, what you do is to get to the delta y is we'll multiply both sides by the delta x. And that's how you get your delta y is these cancel out. You take the evaluated differential equation, that is the slope at the point, and then you multiply it by your increment of x. So in this case, we would have 0 times 0.1. Oh, okay, we got zeros for delta y. All right, next thing you do is you have x plus delta x, and then y plus delta y. This is how incrementally we have moved from our original point of 1, -1. Okay, we are now at 1.1, and our y has not changed. We're still at -1. Okay, that's our first iteration. We're to continue this until we reach an x value of 1.4, which would require us to do 3 more loops of this. So I should just stick with the color. Let me stick with the purple. So our next loop is going to be 1.1, 1.1, and -1. Our dy dx is 1.1 minus 1 over 2, which what is 0.1 over 2? 0.1, it's probably really easy. I'm just having 0.05. Okay, 0.05. Our delta x is still 0.1. So our delta y is 0. What did I just do? Are you guys watching that? What the hell happened? Okay. I moved the whole thing around. Whatever. All right. So we've got 0.005. So incrementally, we have now moved to 1, 2. And our y has finally moved. We are now at 0.995. And that was a negative, because remember, we started at -1 and we've incremented up. Remember, if you think of it graphically, we're actually climbing up the right side of the parabola. So to loop around, it's 1.2, 0.2, and -0.995. And this gets just hairy as far as the computations go. I'm going to stop here, but it's more a matter of bookkeeping and arithmetic than anything else. Put the 1.2 in. Well, let me just keep going a little bit more. I can't stop myself. 1.2 minus 1 over 2. This is going to be 0.01. Our dx is 0.1. Notice how we're sort of climbing up the right side of the parabola. So we are now, did I do that right? 0.00. That should not have been greater. Somehow I think I made it. Oh, This should know. Yeah, nobody's corrected me. Well, I think I had one too many decimals there. 0.2. Oh my gosh, the calc teacher has to use, I have to use a calculator for 0.2 divided by 2. And I still get an error message. 0.2 divided by 2 is 0.1. And our delta x is 0.1. So our increment of y is 0.01. So we are, again, notice we are climbing up that right side of the parabola. We're now at 1.3 in the x, and we are at negative 0.985 in the y. And there I am going to stop. I'm going to pretend that that number said, what's the approximation when x equals 1.3? So my approximation is going to be x equals 1.3, y equals negative 0.985. Okay, and where are we on the clock? I don't want to lose track of time. Okay, 43. Wow, okay. Okay. In order to find a solution to this differential equation, we have to be able to integrate it. This is in a category that's known as a separable differential equation. In order to have a separable differential equation, you've got dy dx, and you have to have an f of x times or divided by a g of y. Your two functions, your functions of f and your functions of g, must be connected either through multiplication or division. You can't do a separable differential equation if you have addition or subtraction of the x and y variables, because what we would, oh, I'm sorry, this should have been a g of y. Okay, because what you would then do is you move the g of all the y stuff you move to the left, and all the x stuff you move to the right, and now you can integrate. All right, that's a separable differential equation. So let's oh good Lord. So let's apply that to the situation at hand. Please set that up. We've got the our differential equation started as and it started as dy dx. If I'm stressing, it's because I think time is going too fast. X minus 1 over 2. To set this up, we're going to separate there's no y's to move. So we've just got dy equals x minus 1 over 2 dx. Okay, nothing going on yet until we do this. Now we're integrating both sides. So what we've got is on the left side, the integral of dy is y. And on the right side, we've got 1/2 x squared over 2 minus x plus c. And you might say, well, shouldn't there be a c on the left side as well? Standard convention is you just, one constant on the left plus another constant on the right is still a constant. So general convention is you put the constant on the right side with all the x's. And this is called a general solution. Okay, now to get the particular solution, I'm thinking was it the ordered pair 1, -1 that we did on the approximation? What you do to get, this is our initial condition. So what we're going to do is we are going to apply x and y and find a value for c. So we got y is equal to -1. And then we've got 1/2 times 1 over 2 minus 1 plus c. Guys, you do not have an answer key, so let's get ourselves through this. We've got negative, so I apologize, what I'm doing is I'm I'm apologizing in advance in case I make a typo here. Correct me if you see something. So we've got -1 equals -1/4 plus C. It's looking to me as if C is equal to -3/4. Okay, so our particular solution is now y equals 1/2 x squared over 2 minus x minus 3/4. Okay, now what we could do is to test the accuracy of our approximation. Now we could apply y at x equals 1.3. Our approximation, if you recall, our approximation was -0.985. This should be somewhere, I hope, close to that. I don't have the answer. I'm not going to spend our time calculating it. So I'm going to move on. This, I believe we've done this to some extent. So, or we've seen it before, I hope. Let's move on to next, which is integration by parts. Integration by parts derives from the product rule of differentiation. Karen Hires, I think, is doing this one. And where is it? There it is. Okay. I'm just going to show you this stupid Zoom tab keeps popping up. Okay. I'm going to show you, and I realize it might be frustrating if you don't have the theory. Ultimately, it comes from at the line at the top. Let me zoom in a little bit. All right, that should be pretty good. The line at the top is our derivative of a u and a v. First times derivative of the second plus second times derivative of the first. If you rearrange those, I haven't got time to show you talk theory. Let me just show you. Here's the how-to. This is integration by parts, x times the sine of x. All right, the first thing you've got to do is you've got to build yourself an inventory. That's the exact metaphor I gave the class yesterday. It's the one I've been given since I've started teaching. The inventory is an x and a dx. No, I'm sorry, a u and a du. We already have x's in the equation. And we need a v and a dv. We're going to rebuild this integral into something that we can't integrate into something we can. And the challenge is and what you need to populate this little this box of information with is you've got to get the u and the dv from your original integral. And I'm going to tell you now for this one, you want to select the x for your u. And I can hear the questions already. How did he know to do that? Just bear with me, we'll get there. And then the dv is whatever is left. And in this case, that would be the sine of x dx. And you should have fully exhausted everything in your integrand as well as the variable of integration. And that goes into this table here. Now what you got to do is you got to take the derivative here, which is dx. And you've got to integrate here, which is the negative cosine. All right. So now we reassemble according to this, this method. We're going to reassemble as u times v minus the integral of v du. Okay, so our integral of x sine of x dx is, okay, u times v, that's x times negative cosine of x minus the integral of negative, I see a typo. Here we go, verbal typo. U times v minus, this should have been v du, right? At least I caught it before you were rewatching it, wondering how the heck did he do that? Okay, so it should be the integral of v, which is negative cosine of x, times du, which is dx. Notice we now have something we can integrate. Clean this up a bit. We've got negative x cosine of x plus the integral of the sine of x dx, and that becomes negative x cosine of x plus cosine of x plus c. Negative. That's a negative there, isn't it? Wait, the derivative of cosine is negative sine. Yeah, it'd be minus. All right. Again, I apologize in advance if I made a typo. I'll be rewatching this myself. So let's go to the next. I know I just overwhelmed you with a bunch of stuff. Let's do another one. Let's do the last one. Okay. Again, we're looking at this. We want to be looking at integrating this by parts. I swear time is going faster today than it did yesterday. I don't know. Maybe I had more urgency and I was able to finish yesterday, and today I am overconfident about completion. I don't know. What we want to do, build the shelving unit for the inventory. We need a U and a DU. We need a V and a DV. Okay, so we have to break this apart and populate the U and the DV. So trust me on this. The U you're going to want to use as your 3x. Your DV you're going to want to use, you're going to have e to the 2x dx. All right, now I'm going to have to do a derivative on this side, which is just 3 dx. And now we're integrating e to the 2x dx. And this is why you got to do u substitutions in your head. If you can't do this one in your head, you're going to have to set up a u substitution and work through all of that. And it just becomes a burden for you. You want to be able to do these in your head. I can see that I need a 2 to integrate. That means I got to pay for it with a 1/2. The integral of e to the 2x is 1/2 e to the 2x. Oh my God, there, 2x. Okay, now assembly is u times v minus the integral of v du. Okay, so the integral of 3x e to the 2x dx is equal to u times v. 3x times e to the 2x over 2 minus the integral of v, which is 1/2 e to the 2x times 3 dx. There's not much cleanup to do on this one. Let me do a little bit. We got 3x e to the 2x over 2 minus 3/2 the integral of e to the 2x dx. Okay, integrating that e to the 2x in my head, I need a 2 to integrate, which means I'm going to balance it with a 1/2. And what that's going to result in, our integral is going to be 3x e to the 2x over 2 minus 3/4 e to the 2x plus c. All right. I know I threw a lot at you. I'm looking at the clock. I've got 15 minutes. I want to get to partial fractions. All right. I did 3 examples yesterday. If you just cut to where I was doing integration by parts, you can see 3 different examples of what. And by the way, I do consider this a basic integration by parts question. We'll get into it gets a little bit more complicated as we go. It's more a matter of just procedural issues. So I encourage you, if I've shorted you guys by not doing as many examples as I was hoping for, I apologize. I encourage you to watch yesterday's class on where we're to the integration by parts section. Okay, last one for our time we have is partial fractions. Partial fractions is a topic that in theory you guys had in pre-calculus or algebra 2. There is very little calculus in this. So again, I don't know to what extent you had this before. Okay, let me just cut right to it. First of all, if you need to integrate this, the first thing you might be looking for is doing a natural log. But in order to do a natural log with that as your denominator, you need a 2x minus 2 in the numerator, and it's not there. And you can't just hocus pocus that in. I think this is a candidate you could do by completing the square, which Karen Hires talks about. This is also a candidate which you could do by partial fractions. Yes, there are two different ways you can integrate this. I'm going to show you the partial fractions way. So what you want to do is, first of all, consider this notion. If I have 5, 6, do you agree that there is some fraction of a number over 2 plus a number over 3, which will get you 5, 6? Well, what are those numbers over 2 and those numbers over 3? Okay, that's the notion of this. So when we look at this, this integral, hopefully you recognize that we can factor the denominator. This is equal to what, x minus 5 times x plus 3. So I'm posing to you the notion that there is some value over x minus 5 and some value over x plus 3 that will complete this. Okay, well, what we do is we gotta act as if we're going to add those two fractions together. So we'll multiply the b side times x. It should have been a minus 5 right there. So we're going to act as if we're going to multiply the b side times x minus 5 over x minus 5. And likewise, we're going to do with the a side, we're going to multiply by x plus 3 over x plus 3. Basically, we've set this up as we're going to add these fractions together by getting common denominators. Now, the key is you look just at the numerator. If we look just at the numerator of this entire equation, because the thing about it, the denominators all the way across are x minus 5 times x plus 3. So in the numerator only, we've got 1 equals a times x plus 3 plus b times x minus 5. Now, instead of getting into a real fancy systems of equations thing, just come up with a value of x that gets rid of either a or b. Well, I'm looking at that a times x plus 3 will let x equal negative 3. When you do that, you get 1 equals a times 0 plus b times negative 3 minus 5 is negative 8. So b equals negative 1/8. All right, let's find a way to get rid of the b. What value of x will make b go away? Applying 5 to this equation, we've got 1 equals a times 5 plus 3 is 8 plus b times 5 minus 5 is 0. And we have a equals 1/8. Notice I haven't done any calculus yet. Okay, where this takes us to is I need to erase. So this is all going to go. And everything I'm erasing is I don't want to say you've done this before, but this is something that curricularly resides in pre-calculus, right? So what you've done is you've taken 1 over x squared minus 2x minus 15, and you've rewritten it as 1/8 over x minus 5 plus negative 1/8 over x plus 3. And if you don't believe that works, add the two fractions on the right side together by using common denominators and see if you don't get that. So what we got to do is with the whole purpose of this, and here comes the calculus, we are integrating this. dx. And hopefully you guys see that this is a pretty basic natural log rule for integration. We end up with 1/8 times the ln of x minus 5 minus 1/8 the ln of x plus 3. Let's see. All right, and that is a fully correct answer. I have about 8 minutes left. The thing I will say is that is not likely the way the answer would be represented on a multiple choice question. Let's see, I could factor out the 1/8. And I'm gearing up to do a properties of natural logs. A quick review here of what you should know is that when you have a difference of two logarithms, if I have the ln of a minus the ln of b, that's equal to the ln of a over b. And just to complete this, if you have the ln of a plus the ln of b, that's equal to the ln of a times b. All right, so I'm basically, we're getting a little into the weeds here, but I'm just showing you how a multiple choice question would likely look. This would be 1/8 times, well, if you needed the ln of x minus 5 minus the ln of x plus 3, which is going to be 1/8 the ln of x minus 5 over x plus 3. And that is an integration by partial fractions. It's relatively calculus free until you get to the end. And when you get to the end, it's kind of easy. All right. I think I got time for one more. Let's see. Any of these grab me? Well, can we do these when there's an x in the numerator? Yeah, sure, we can. This is kind of come at the expense of that last one, which is also a good one. There it is. Okay, as we size this up, I might be tempted to do a u substitution and apply a natural log. But if I'm going to do a u substitution, I'm going to take out the x squared minus 1, which means I had du dx equals 2x. And I don't have that in the numerator. Now I could sort of finagle my way through. I could create a integral of, I'm kind of getting into the weeds here. I got an x over x squared minus 1, which I could actually see that part being done by u substitution. What are you going to do with the second part? Because we've got minus the integral of 2 over x squared minus 1. So this is the one you can't do a u substitution on. It looks like, well, maybe we could do one of the inverse trig functions. Nah. Basically, this is one you've got to be using partial fractions. I think you could do a completing the square. Because we're talking about partial fractions, I'm going to go that direction. So factor the denominator, create your separated fractions. Here, this is what you need. X minus 2 over x plus 1 times x minus 1. And that is a over x plus 1 plus b over x minus 1. And you might be asking, well, what if I put the a over the x minus 1 and the b over x plus 1? It doesn't matter. It'll work itself out as long as you stay consistent. So what this resolves to is x minus 2. Again, we're acting as if we're going to add those two fractions on the right by getting common denominators. So that would be a times x minus 1 plus b times x plus 1. And we're going to ignore what's going on in the denominator. So what we want to do is we want to get a or b to go to 0. So we will let x equals 1. And now we do have something going on the left side of the equation. We've got 1 minus 2 equals a times 1 minus 1 is 0 plus b is 1 plus 1, which is 2. So we got -1 equals 2b. So b equals -1/2. Okay, now to get rid of the b, let x equal -1. I've got 3 minutes. I'm on the clock. So we got -1 minus 2 equals a times -1 minus 1 is -2 plus b times 0. We get -3 equals -2a. Okay. I don't have an answer key. So I'm just, so a lot of times when you do partial fractions, there's a symmetry between the a's and the b's. And I was kind of in my head expecting a equals 1/2, but unless I did a typo, it looks as if we've got a equals 3/2. Okay. So let me get rid of the non-calculus part. This is no, this is technically, this is a pre-calc topic. I know you guys were shut down in the spring and you didn't have a chance to go through a lot of things that I wish you'd had a chance to see from Elioth or whoever was teaching you. But here we are. So what we've got basically is that this integral has been rewritten as the integral of, now be careful, make sure you put the a over the right denominator. We've got 3/2 over x plus 1 plus -1/2 over x minus 1. Yeah, you could have written as -1/2 over, I know, just this is how I do it. So this, again, here's where we are. We did a lot of prep work in order to get us to where we can integrate, and we are there. Very easy natural log integrals. We've got 3/2 the ln of x plus 1 minus 1/2 the ln of x minus 1. There might have been a verbal typo somewhere in my presentation over this last hour. If you watch the replay of today's class, which will be in PowerSchool, fine, I make mistakes, but the theory of what I talked about is sound, okay? We are at time in a minute. Let me think. I think we're good. All right. As usual, message me if you have any questions. Get after those videos, topic questions on Friday, and you got parts and partial fractions are waiting for you as an ebook assignment on Sunday. This was your first exposure from me to them. I'm pretty sure that the videos you're going to be watching are a similar topic. All right. So I am going to stop share, but I will edit your guys. You know what? I'm going to stop the, I don't know how to stop the recording. Let me see if I can do that. Right. Am I still in pen mode? I just want to say goodbye. Stop.